Now let's just work a bunch of problems using those rules we learned about in the previous video. All right, so got to do the derivative. Also, make sure that you're telling yourself when you're starting to do the derivative, because sometimes you're just going to be rewriting, or you'll have to rewrite first, then you'll do the derivative. So you need to keep yourself organized and understand where you are in the process. So for question number 1, I'm ready to go do the derivative. So I'm going to use that notation for a derivative. And f prime of x would just equal 0, since the original function was a constant, and so we know the derivative of a constant is 0. Okay? We know that because f of x equals -9 would be a horizontal line, so its slope would be 0. We also know why that rule has to be what it is, because you could think about this as being the original function as being that, and then use the simple power rule to see why they made it, why they told you that it would wind up equaling 0, and that's because -9 times 0 times anything else is going to be 0. Okay, but you don't go through all that. You just know that the derivative of a constant would be 0, and the best way to remember that is to think about how this is a horizontal line with a slope of 0. All right, now for question number 2, that's a one we're ready to jump in and do the derivative. They used y instead of f of x, so I'm going to do y prime. I try to avoid writing an x to the, or a y to the first power now that we're using that notation. Okay, so anytime you see that, it's not an exponent. I try to make it a little more at an angle. It's that prime symbol that can be used for derivatives. So we're going to bring the 12 down, and then we're going to subtract 1, and that's going to wind up being 12x to the 11th. Okay, and when you're ready, just jump to right there. Okay. All right, now both 3 and 4 need to be rewritten. So this is where knowing your exponents can help. So I'm not doing the derivative right now. I'm just rewriting the expression so it looks like a power function. And so for the x to the 7th to wind up in the denominator, it had to come from 3x to the -7 power. So now when I go to do the derivative, bring the constant along. Okay, the exponent comes down in front, and then I'm subtracting 1 from the exponent. So that becomes -21x to the -8th power, and then you're not allowed to leave negative exponents ever. Well, I'll say most times. Sometimes a problem will start with a negative exponent, and in that rare case, it's okay to leave negatives. Okay, so your answer would be -21 over x to the 8th power. Okay, now problem number 4 needs to be rewritten before you can do it. So you need to think about how 4th root of x is the same as x raised to the 1/4 power. Now that it looks like a power function, we can do 1/4 x, subtract 1 from the exponent, and we wind up getting a -3/4, and then we'll rewrite that using radicals and also getting rid of that negative exponent. So it'll be a 1/4x to the 3/4, and that would be the same as having a 4th root, because that comes from the denominator, of x, and you could put the 3 there, or it's the same as putting the 3, let me write that more clearly. It's the same as if you did the 4th root of x and then cubed it. So that's okay also. Okay. All right, now 5 and 6, 7 and 8 are all polynomials. So you'll just do the derivative of each term, because when you're doing derivatives, it is okay when adding and subtracting is involved in between things. It is okay to do the derivative of each term. And so on these, you'll just think the derivative of 6x is 6, the derivative of 3 is 0, so this is going to be 6. Okay, on question number 6, The derivative of t squared would be 2t to the first. Derivative of negative 3t is negative 3. The derivative of 1 is 0, so 2t minus 3. Okay. Y prime of number 7, when you do the derivative of 4x, you get 4, and the derivative here would be negative 9x to the second. Okay. And for number 8, the derivative of the first term would be 2 times 3, which is 6x to the second power. And then second term would be 12x to the first power, which I'm not going to write the 1 on it. And then the derivative of the constant term would have been a 0. So 6x squared plus 12x. It's that quick. Okay, it's that fast to do. All right, now, you'll sometimes have problems like these, where you need to do some rewriting. They talk about you putting it in the table, doing it in a certain way. What I'm going to ask you to do is just make sure that you're clear about when you're just rewriting and when you are actually finding the derivative. Okay? So get used to putting in, telling yourself when you're starting to do the derivative, like I was on these. Okay? So like on number 9, I have some rewriting to do. First, this is the same as 3/2 times 1 over x to the 4th. And we know that a 1 over x to the 4th is the same as x to the negative 4. All that's just rewriting. Now, when I go to do the derivative of it, I'm going to bring the negative 4 down in front and subtract 1 from the exponent. Now, I'm writing a little more on that problem than I did on, say, question 7 or 8, because the exponent was negative and my coefficient was a fraction, so it's just harder to do. All right, now 3/2 times negative 4 would be negative 6, and then negative 4 minus 1 is a negative 5, and then my final step will be rewriting that. So the negative of 5 is applying really only to the x, so the negative 6 stays on top, and then we have negative 6 over x to the 5th. Okay. So you need to be, really working on making sense of those exponent definitions and properties, okay, and then using them correctly. All right, now with number 10, we don't know the chain rule yet, but we could still do this problem if we take a moment to take 3x and square it, which means this. So you really have a 9x squared. And then we can do a similar thing to what we did on the previous problem. Then we really have this constant, pi over 9, multiplied by 1 over x squared. So that's a pi over 9 with an x to the negative 2 power. So the derivative would equal pi over 9 times the negative 2 times x to the negative 2 take away 1. So that's negative 2 pi over 9 x to the negative 3. So that's negative 2 pi over 9, and the x to the negative 3 would be moved to be down in the denominator. Okay. All right, now sometimes people misunderstand the difference between a negative exponent. A negative exponent does equal 1 over that, but a negative number is just a negative number. It doesn't mean 1 over something. Okay, it means that you have negative 1 times something. Okay? All right, so let's do these couple of problems, and then I'll stop the video. Okay. All right, so these are actually ones where you'll first simplify. Since there's a single term, okay, I can go ahead and think about this as 4x to the 3rd over x plus 2x over x plus 5 over x. That would be true. You normally would go right to this idea that means I can knock out 1x from each of those terms. But that last term is 5 divided by x, so there was no x to knock out, and I'd like things to look like power functions. So I'm going to think about that as being a 5x to the negative 1 power. Okay? Now, once you get to there, once you get to here, you got your little mini power functions. Now you can come in and do the derivative, and you'd get a 4x squared, you'd get an 8x plus a 0, and then negative 1 times 5 would be negative 5x to the negative 2 power. Now you will want to go ahead and get rid of the negative exponent and clean that up a little bit. And so that one would turn out to equal, let me get a line here, that's the previous problem. So that would turn out to equal 8x minus, and the negative 2 applies only to the x, so that would be 5 over x squared. And it's typically acceptable to just leave it like that. Okay, now you may have some issues when you try to compare your answer to the answer in the back of the book, because they might have put together these two terms by getting common denominators. So for instance, this would be the same as 8x to the third over x squared minus 5 over x squared. So another answer you might see is this, and these two things actually say the same thing. But this is widely accepted, okay, as a perfectly good stopping point. All right, so let's finish these. You're going to distribute first. So I'm not doing the derivative yet. I'm just rewriting so I have my little power functions in front of me. Then I can take the derivative quickly and easily. 2 times 4, 8x to the third. 3 times 3 is 9, minus 9x squared, and I'm done. Okay. Now, this one, you have fractional exponents. So they're already written like power functions, so I'm ready to go in, do the derivative. This one I might write a little, if I have t's, I need to have t's, or if I have x's, I need to have x's. So let's fix that and make it a t right there. All right, then it would be 2/3 t to the 2/3 minus 1 minus 1/3 t to the 1/3 minus 1 plus the derivative of the constant, which would be 0. So here what I have is a 2/3 t to the negative 1/3 minus 1/3 t to the negative 2/3. You can do fractions on your calculator, so no reason to be worried about that. You'll be able to do that quickly and easily. All right, and now I'm going to take and rewrite those. So this would be the same as 2 over 3 to the 1/3 power. I left out the t, so let me do a better job of that. 2 over 3 t to the 1/3 power minus 1 over 3 t to the 2/3 power. Okay. All right, now it started with fractional exponents, so you would probably stop there. But in reality, that original expression was actually the same as the cube root of t squared minus the cube root of t plus 4. Okay, that's what the original expression really was. And what the derivative might look like if you put the radicals back in would have been 2 over 3 cube root of t minus 1 over 3 cube root of t squared. Okay. All right. So if it's typically, the rule of thumb is if it starts with radicals, then you need it to end with radicals. But if they have fractional exponents in the beginning, then it's typically okay to have fractional exponents at the end.